been researching the causes and behaviour of drinking water discoloration for the last 15 years. So he's...
he looks all right.
he knows a bit about it. He's designed and built a full-size laboratory which has world-leading facilities and which can be used to look at microbial problems, turbidity and biofilm development, and has also carried out field trials across the UK and internationally. He's also developed models to identify the development of discoloration, and has helped UK water companies develop multi-million savings and improved water quality. So he's the man to go to for water quality. Apart from that, he's got a degree, a master's in chemical and bioprocesses engineering, and postgraduate degrees, and a few other qualifications. So over to Stuart to now talk about smart networks for condition monitoring.
Okay, thank you, Joe. This will be a slight deviation, maybe from looking at what you've been considering when we're talking about condition. I'm very looking at the qualitative side of things. In other words, it might not be necessarily your field of work, but even if you don't follow, it does affect us all because it's the water we drink. So there's a lot of general interest. Now, as Joe said, I've been a researcher, so I'm lucky. I'm not an academic, I'm a researcher, so I've been able to spend the 15 years purely looking at this topic, not distracted with teaching or anything else. I have worked with all the companies in the UK and currently still am. So, as a researcher, I've been very lucky at Sheffield. We're part of a very large group, so I have a lot of expertise to call on as well. So we have a lot of different parts within the group, a lot of experts in road infrastructure, different sensors, and also with social aspects as well. Some of the projects we're working on, you may have heard of, you may not. I've just got three to highlight. By 2065, this is a large research council-funded project, hopefully looking to the future, trying to examine what's going to happen with water supply in the future, where it's going. It's a number of universities all linked with that one. We also do a lot with Europeans, so this is Smart Water for Europe. Again, this is 23 companies involved in this across Europe, heavily involved with Thames Water, looking at different monitoring strategies, what's going to happen with monitoring, how it's going to help, where it's going. One particular project that is maybe very much interest is called UKSTT, and at Sheffield we have the National Laboratory for Distributed Water Infrastructure. And basically this is going to be a 1,200 metre cube tank in which we can lay pipes and then we can put them under all sorts of different tests, whether it's complex cyclic surface loading, different flow regimes, all sorts of different strategies. That's currently being built. It's hopefully completed in 2018. So that is open for research, and so there's a lot of ideas coming on that. So that is probably very relevant to what a lot of you might be doing, might be involved with. UKSTT, strange name, UK Collaboratorium. I think they've been making words up here for these acronyms, but there we go. So that's a very interesting one going up there. So a huge big project, part of £138 million government initiative, 14 universities. Okay. What I'm talking about, though, and my speciality, is a project called PODS. Now, when it was first started back in 2001, nobody ever thought it would go anywhere. So the name PODS, who cares? It's a throwaway name, it'll do for the project. But the project has just snowballed, it's kept growing. It also says a lot, it's now very much in the impact stages, research into impact. But it does say how long these ideas can take to get accepted and taken on board. Now, the PODS project, we're in stage 6 at the moment, and hopefully we'll start stage 7, or we're going to rename it, brand it slightly. But it started off this project as an idea, a concept, tested it with a couple of companies, and it seemed to work. It did work. So we've took it out to more companies, and these were just in the small pipes, distribution pipes, and since then it's rolled on and on to the bigger pipes, and now we're very much looking at how we can get the companies to use it and implement it. Involved with many companies. Right, so the value, why? Why is this still going? Okay, this was Scottish Water magazine from last year, June 2016. They did an article on pods, might work, I'll work in them. And they claimed that using this pods would make a £15 million saving. That's in their current AMP cycles, that was about 2 years. Also, same customer outcome, lower cost and service risk. September last year, Northumbrian Water and Wastewater, and I didn't know about this until I was informed, published an article saying that using pods, they'll get improved service and 90% capital cost savings. Now, when they're talking about projects in excess of £100 million, I think you can work out your own maths what sort of savings they're talking about there. Okay, so how do we get to this? What's actually happening? What's going on in these pipes? What they're doing? Okay, I'm going to focus on discoloration. It's what we see, what the customers, as we open our tap, what we might see. Now, the reason that's important is that the water companies are now being judged on it. So you can actually go online, there's a site, Discover Water, and you can click on, and it shows you how each of the companies are performing, both this year and the last few years. Discoloration is, they say that was in 2013, the previous graph, they reckon 2.9 million people will have been affected by it. Now, their league tables, this has huge relevance to their credit ratings, and as they're all privatised companies, it's very interesting on performing well. It is interesting, I'm not going to go into the details, we've split the chart up. All the companies doing very well are those in this bottom corner of the country. Very different geology. We'll come back, that links it all ties into water quality, which will keep coming back to on water quality. Okay, so I've got some questions for you to make sure you're awake after lunch. Are zero discoloration complaints possible? Okay, A, B or C, so it's not too difficult. I'll give you a choice, multi-choice answers. Anybody want to go? Are zero discoloration complaints possible?
Either.
No, you reckon, no? Right. Yes, I would go, well, let's go right. The answer is yes. For a start, each water company could just deliver bottled water. That's a solution. That could work. And they could check each one, there'd be no complaints. Brilliant. However, we don't deal with that system. We have this pipe network where there are all sorts of things going on. And when you learn a lot more about this network, I think it'll be impossible to go for zero complaints because of the complexity, which I'm going to hopefully explain. Okay, next question, we've got that bit. Now, discoloration keeps coming back. So, to minimise this risk, what should companies do? I'm not making it difficult, these questions. I know it's in the afternoon, we're down in the dungeon here. What should we do to minimise risk? Right. Again, this is interesting, because someone had this earlier today. If there isn't a problem, and these networks are doing fine, and there's no changes planned, then I would say do nothing. If it's working fine, why do anything? You don't have to do anything. If there's a known issue, or there's a change planned, and that change could be you're rezoning a network, or you're worried about a burst potentially, then you may need to do some sort of maintenance, some sort of preventive action. Okay, so what is this PODS concept? This is a picture from them. This is the D, this is United Utilities main, they took it out for cleaning. What we said, the concept is very simple, is that material builds on the pipe walls. Now, in normal systems, we do not see sediments. It is not a sediment issue. It's not a gravitational issue. You don't see stuff set to the bottom of the pipes. This stuff grows up all the way around the pipe walls. Okay, so it's a non-gravitational process. We never said what the process was. We just said this stuff sticks to the walls. Okay, and it happens in any pipe. We said these layers of material are then conditioned by the hydraulics. Again, that's cool. If you've got a high flow going through the pipe all the time, you don't get a lot of material. If you've got low flows, this material can get more and more of this material building up. Okay? And what we said was this material is eroded or immobilised when the system shear stress, when we talk about shear stress, which is the force, rips this material off the wall, and because it's fine and particulate, it travels through the system. Okay, I mentioned shear stress there, so I'm just going to, go back. So you might like this, but this is relevant. This is inside a pipe. If anyone's been up to, if it works, do I have to press play? Should work. It did work earlier. Oh, there we go. If anyone's been up to Ladybower, Severn Trent Water, there's Bamford Treatment Works. There are twin pipes coming out of it, and this is videos from inside the pipes during operation. So, what you can see, this is the bright light. Going down the pipe all the time is these very fine particles. Now, you wouldn't see these with your naked eye. They're very small, but because it's a bright light, it's the light being reflected off these particles. Well, that's what turbidity is. If people talk about turbidity when they're measuring turbidity, it's the amount of reflected light. And what we can see from these pipe walls, this material is building up. So we have this continual movement of particles down the network. Some will be attaching, and some might break off, but all the time we're building up these material layers. Doesn't matter what pipe we're talking about. There's a parallel pipe next to it, so this is a 45-inch cast iron pipe, slightly more tuberculated. It's still got the same effect, it's got this layers of material building up, the tuberculation. And the cast iron, of course, has a hugely negative impact. I don't know what some of these features are in the pipe, but we'll just take whatever that was there on the side. Cast iron are extremely negative because they produce a lot of particles, a lot of iron. So there's an interesting point here with cast iron pipes. You might have the best treated water in the world. You run it through a cast iron pipe that's corroding. You might as well have someone there just shoving material into the water. And this then travels downstream and affects everything downstream. So we're almost getting to the point now where we're thinking, hang on, we should be looking to replace cast iron pipes on a quality basis alone now, irrespective of quantity. Okay, now I talked about shear stress, and again I want to just test your hydraulics. Those of you who don't hydraulics, quick, simple question here. This was from Northumbrian Water, this is north of Newcastle. A large main, and at the top, I picked these numbers to illustrate the point. They're 100 litres a second, down the bottom 10. They wanted to do some extra work, so they wanted to get from 10 to 20 at the bottom, 100 to 100, so it'll be 100, 110 to the top. So, it's a 100% increase in velocity or in flow rate at the bottom, just a 10% increase at the top. If you were thinking, right, we know there's materials in the wall, it's going to be washed, if we increase the flows, we'll take the material off. Where's our risk going to be? Where would you say the risk is going to be? 100% increase in velocity or a 10% increase in velocity? Where's the risk? Of course, it's a trick question to don't worry. Right. Well, Northumbrian Water, 100% risk. We've got a problem. They put monitors out. They adjust the valve, there's a bypass valve they were working on. Monitored it, no real problem, fantastic, packed up, went home. That night they got 1,000 odd complaints. The DWI reckon there were about 140,000 people affected in the top section. Why is that? Right. Those who want the actual numbers and figures, here's the actual numbers for the actual say. The top one shows the velocity, so the A is the top section, B is the middle, and the green is the bottom section. So the velocity clearly shows the bottom section was higher. When you consider the forces of the pipe wall, I'll explain what they are in a minute, clearly the top section was far worse. So what do I mean when we say forces? I like to use analogies. Let's take a car. You put it this way. You go from 10 to 20 miles an hour. It's quite easy. It doesn't take a lot of energy, does it? You go from 100 to 110. Stick your car, hand out the window, you know this. There's a huge amount of extra force and energy required. And it's that extra energy, the force, to overcome the turbulence. And this is exactly the same in the pipes. We're looking at the head loss on the pipe wall. So that extra increase of the force is lost, it's turbulence on the pipe wall, ripping this material off. So that all this material is trying to hang onto the wall, and the hydraulics is trying to rip it off. So there's a simple force balance. And that, in essence, is what the whole concept is. Okay. So, if you actually see it in action, on a normal day-to-day basis in pipes, you never have a problem. So if your system operating normally, brilliant. If you increase the flows, for whatever reason, what you then get, as the flow increases, it strips the material off the wall, this is fine material, travels down the system, and you get your drinking water, it's brown, you complain, and there's all sorts of problems. Okay? That's simply it. So, moving on, I can do some examples of this. So this is across in Wales. This is North Wales, Abergele. And it's great because this is a lovely section of trunk main. We've got different monitoring points. And had previous issues were in there. And what you see, if you increase the flow is the red line, and we can turbidity at different points. A very consistent increase as you travel down the pipe. What's more, you go back 3 months later, you get an identical response. So this material is coming back. And we know it comes back at almost a steady rate. The PODS model is a very simple model we developed. As I said, all it is a force balance. And then it's an empirical model, so we worked out the force balance, and then we went out and did trials, and we work out what the changing forces relate to in terms of stability. And it fits very well and very nicely. Using the same parameters one model, we can fit it to the next trial, and we get the same fit. So this PODS model works. Now, it doesn't just work in this section. It's worked on cast iron pipes, it's worked on plastic pipes, it's worked on pipes from 2 inches over 2 meters. A simple concept of material building up. Now, one of my favourite bits we're getting to is, what is this material? There's a link here. This is at the bottom here, links to why Northumbrian Water said they saving 9%. They went and cleaned all the pipes. So they physically went in, did some sort of invasive clean, found all the pipes around Newcastle. 4 years later, and that cost £70 million, it was a project £70 million. 4 years later, all the problems they went in to clean against were back. Same number of complaints, the same issues. So that effectively, there was other repairs and things as well. But in terms of water quality, they hadn't achieved anything. Within a few years, it was wasted. So the saving they're reporting now is they had these big projects planned, they've actually put them on hold until they've got follow-up strategies to make sure they can keep the systems clean. So it's not quite as simple. Okay, so what is this material? Here's a bit of clean pipe, sterile pipe. This is plastic pipe, you see the extrusion lines. We say they're smooth, they're not smooth of course. Within 28 days it looks like this. This is all biofilm. So what we are talking about here are very much ecological systems. These water pipes are living biological systems. And here we've got primary cells attached, and what they actually do is they produce something called EPS. It's carbohydrates and polysaccharides in the chains. It's like a scaffolding structure. They produce a scaffolding structure, and they communicate, but then they grow these large biofilms. So it sort of look like this in the end, with all the cells, and it's full of channels and pores. So you can imagine there's a huge community of living on in here. All sorts of nutrients being taken out and everything else. And within this matrix, developing the biology, any other material, iron, manganese, any other chemicals that might be floating around the system, get trapped and embedded in it. So when these are eroded off, it's often this iron and manganese that are trapped that cause the problems. So once you go back to cast iron pipes, you can have a section of cast iron pipe, and it can be affecting everything downstream. Because this iron's coming off, and this iron gets trapped, so you get actual pseudo-iron behaviour. Okay, so these systems are living biological systems, and I would say thank God for that. The reason I think it's essential that we have these biofilms in, for a number of reasons, but just very briefly, these biofilms are hugely protective. We're organic organisms as well. I think as humans, we take a lot of nutrients from the water supply, it's coming off the wall, but more importantly, this particular biofilm, they're adapted to live in these very harsh environments, with chlorine, it's dark, not a lot of nutrients. So these are specially adapted. They prevent other organisms that may be more pathogenic to us from surviving. They're using all the nutrients, they're preventing these other things getting in there, so it's providing a safety factor to them. I like this biofilm to be present. So if I say a pipe is behaving fine, I don't want anybody to go in and do anything with it. I don't even like going in physically, putting the cleaning methods in particularly either, because then, to me, that's only the potential that you're creating specialist niches where pathogenic organisms or other biology could get in. Now, we know we are sensitive to the water. I'm sure all of you have been abroad on holiday. The water's fine, people drink their water, but we go abroad, and there's a transitional period where our body has to adjust to it, and it has some undesirable consequences. these pipe systems are exactly the same. You go put any change in, there's a period of transition. Now I'm lucky, I've been studying hydraulics. Hydraulics is great because I can measure it, I can measure the flow, and it's the same here in the UK, in Australia, in America, wherever. I get the same response. I can measure it. Of course, I could also look at maybe the chlorination or changing the water, but then this becomes very site specific because each site behaves slightly differently. Each site is adapted differently. But these are living systems. And it's not far away we'll start to think about health. The iron, people might say in the future the iron's useful. If you're pregnant or anemic, you might want a system that's run through an iron pipe. Okay, lucky at Sheffield, we have a rig to test all these. Full-scale rig, this is 600 metres of pipe. We can put coupons in, we can take out for analysis. I won't spend much time. We did chlorine tests. Strangely enough, we repeated it because the results shocked us. The higher the chlorine levels we put in, the worse was the discoloration. Because that's a 3 loops we can compare different experiments. So we had one experiment, one with a lot of chlorine, normal background chlorine, and removed the chlorine. And the one with more chlorine actually produced higher discoloration. We don't understand whether we've got theories to it, still looking at it. Interestingly enough, the one with more chlorine though had fewer cells. So what we think happening is actually, although there are fewer cells, they produce a much more firmer matrix, more scaffolding, this EPS scaffolding, that allowed more material to get trapped in it. And the fact that you change the oxidation can affect the precipitation of iron as well. So there are a couple of factors. Again, Severn Trent going down from Bamford, we can actually track the number of cells, we can count the number of cells. As you travel further, as the chlorine drops, we see cell counts going up. So we know cell numbers are affected. There's huge things going on, how it all changes. It's a complex system. And what you have, this is just a 3D representation. We did the analysis, if it will work. I've got a thing to work here. All it is this is just taking off, and the different colours represent carbohydrates, proteins. This is the biofilm on the surface. The biofilm isn't homogeneous. You may get clumps of type of bacteria here, different bits there. So our modelling wouldn't work on the microscale, but because the surface area in these pipes is so big and these pipes are so large, it does work as an average. Okay, how am I doing for time?
Yeah, you've got fine.
Okay, thank you. Right, so another way of looking at this, what's inside our pipes. This is coming from the latest research now. This is where we presented the companies last week, and this is where they're really getting interested because we can start putting costs and things now. There's another way of looking at it. So if you take the y-axis, what we're saying is this is material present on the pipe wall. So at 0% there'll be no material, and 100% there's as much material as the system can handle for the hydraulics. So what we're saying, on a normal day basis, you get this sort of peak flow. Tor is the shear stress, but it could be flow or velocity. So on a normal day basis, you don't get any material below your peak velocity. Not that you really notice, a small amount. Above it, you have all this material built up. So what then happens with companies is there's some sort of event. It could just be some pop concert going on somewhere, or it could be burst, or it could be them doing a rezoning. And in most cases, most instances, the company's own doing. If you have some sort of event, and not surprisingly, this material gets mobilised very quickly. It takes a matter of minutes, maybe hours to do it. If you're inside at an angle, like that, it's because we're looking at a force balance. So this material at this end, the force is the difference between the two, but at this end, this is that force. So this material gets eroded a lot quicker. That's those who do the maths. So we go through eroded material. And then what happens is, because we have this constant flux of material, it starts to build up again. Now it's interesting, this accumulation rate is directly related to your water quality. So if you can improve the water quality, better treatment, removing iron pipes, you can reduce this accumulation rate, which straight away you think, well, that extends my maintenance frequencies, the times I maybe have to go back and do some work. So after a period of time, we're back to maximum risk. And what's scary is now, you'll see in the next few slides, this is taking about 12 to 15 months. And some of the worst, the pipes are considered risk pipes. Okay, so what we actually have going on then is you start with this material, you have some event, mobilised material, starts to grow back, then there might be another smaller event. So what we can see is a whole different set of bands going through, where some have some material generating, some materials being mobilised. There's all these bands. So what we're now doing with our modelling is now splitting all this up into different bands to examine it. Okay? So all these bands are at different states. Okay, have you been paying attention so far? Quick test. Now, here's the question. This is what companies are looking at. To maintain a desired resilience flow. Now that's, when I go to companies, talk about this is the biggest problem. You say to them, well, what flow do you want to put down this main? And I've called it resilience. What's the target flow this main needs to do? And that's such a hard question for you to answer. Because they go, well, are we looking at what peak flow might have been? Have we got the records? Or are we worried about bursts? But for the sake of this question here, I'm saying this is a target flow. You want it to achieve a certain flow without causing a risk. Okay? So, which strategy gives you the lowest discoloration risk? Put a new pipe in or relining it. Do some sort of invasive clean strategy. Swabbing, jetting, pigging, whatever. Or flow conditioning, where you're just using the flow to manage this material layers. Which one gives you the lowest discoloration risk, A, B or C? Okay. Any? You all got your answers? I won't ask you for it. Huh? You pick A, B, C. They're all exactly the same. Makes not a jot of difference. I'll explain why. Here's your pipe with all the layers on. You put a new pipe in. Bounce back, as clean as anything. It's only clean for a second until you put water in. As soon as you start putting water through, this stuff starts to grow. It starts to You do invasive clean, hopefully you get rid of most of the material, there'll always be a little bit left. It might be fantastic, you might get rid of it all, but anyway. You do some sort of flow conditioning where you're managing the flow, you just achieve your target flow. Okay? But in all cases, the risk grows back at exactly the same rate, and you're worried about this risk zone. So it doesn't matter what you've done. And over a period of time, this risk is still growing all the same. Be it a new pipe, relined pipe, cleaned, or just managed with the flow. Now, of course, what there is a huge difference in the cost of these. So you can understand where companies are now saying, well, hang on, we thought we had water quality problems in this pipe. We don't need to reline it, we don't need to go in and clean it. What we can do, if we manage the flows, especially if we put a valve in or some sort of control valve, we can do it automatically, we can actually manage the flows by some guy just sat at a desk, just pressing a button every so often. And in fact, some companies have done it automated. So basically they just have an algorithm written where all it's doing is checking what's the flow been in this main, what should it have been, okay, I'll increase the flow automatically. So again, this goes back to filtering water. They plan to do loads of invasive cleaning, maybe relining. They say, well, hang on, there's no point in doing that unless we have some way to manage the flow afterwards. This is why they put it all on hold. Because otherwise, you spend your £100 million, 3-4 years later, it's back again. Is that sustainable? Okay. I'm not saying invasive cleaning isn't valid. If you've got an historic legacy of huge amounts of very poor treated water over a long period of time, yes, I think it's probably advisable to go in, get it all clean to start with, so at least you know where you're starting from. Okay, and operationally then, we have the cycle, material constantly eroded, and we're drinking it, it's lovely on the whole. If you've tasted sterile water, it's got no taste, it's horrible. In terms of discoloration risk, there's no such thing as a clean pipe. So people say in the industry, oh, we've got a clean pipe, we want that pipe cleaned. No, can't do it. What you can do is make it clean or fit for purpose. This discoloration risk depends on just two factors. So the water quality, and I talk about discoloration, but within the discoloration you've got iron and mac and all these other things and potential for all sorts of pathogens and all the rest of it. It just depends on two factors. One, how much material is there, how long has it had to build up? And two, how big is this change you're applying? Now, interestingly enough, when we used to have lots of bursts, when the systems used to have more bursts than they do now, should we say, there were far fewer discoloration complaints. Because nothing like a good burst in the system to strip it all out and get rid of all this material. And this also reflects a lot of the industry now is looking for, they're saying calmer networks. So they're suppressing flows. So when you suppress these flows, you allow this material to grow bigger, and it also makes them a lot more sensitive to any change. So really, when we talk about calm networks, we should be looking at reducing the transients, potential transient effects. We should still keep at least diurnal change in flow. So of course the other operational thing is that any type of cleaning strategy is only ever temporary. Okay. Now, just the current research then. I'm going to very briefly touch on these. We've called a variable condition discoloration model, another catchy acronym. Again, one of these things got in stuck. And I'll just mention machine learning very briefly. Okay, some examples. This is from South Stats. This is 5.5 kilometres of 500 mil main. Here we have the flow profile in blue, the measured turbidity at the ends, down that line at the end here. And what we're going to do is put this model, and what the model does is just split it into chunks and adds up all the results. So, the top represents the same as the flow profile, but it's just the shear stress because it's exactly the same. What this chart shows you, I've taken 3 example bands. We're going to show you the different bands. And what you can see is where it's from 0 to 1. So when it starts, I've got no material at all. It's effectively the same as a fully clean pipe in this one. And these bands, materials regenerate. So this band here, which is quite a well attached band, is growing until there's a large event, at which point it mobilises the material. And when you mobilise the material, you then get a response in the model to produce the response. So this bottom plot shows the blue is the measured value and the red is the model response. Now this company, we're going in and doing, these are intentional flow trials. 3 flow trials going on to do the work. And what you do, if you pick these flow trials, they're running them over 2 days, and what they do is they increase the flow slowly. Well, you know increase the flow moves material, so I always think, well, you do that in managed small steps. If you do small changes, and you're monitoring it, you can actually manage it, and you use it to our advantage. So that is what we're actually telling the company to do now. You can manage your flows, so by doing these small steps, you can actually get to a point where you can have these high flows without a risk, without a problem. And you know you can go back to these high flows within a certain time period. So we can look at the model. It's not perfect, but we're talking 0.2 of an NTU. 5 years ago when I was out there measuring, if I could measure to 0.2 of an NTU accurately, I was happy. Now I'm modelling to far less than that. There's been a huge change in the quality of instruments available for online monitoring and in place. But it's not just there, it picks up all of these events, this model. So downstream we've got these other events, and it's matching them reasonably accurately. It's certainly accurately enough if you want to do some sort of engineering planning. Take another example. I'll just put this in. We have a set of parameters. Regeneration rate in this case is 1 year. Pipe length. This was the site I showed you earlier, the Wessex Water site. We were lucky to do 4 independent trials back starting in 2014. So they've now got online data, so it's the red line. It's the plot. And again, we can pick up 4 independent trials. I'm looking at this bottom graph here, the fit. You can see where it's fitting over this time. This is over 3-4 years. What's interesting, these parameters I'm using in the model are exactly the same as the last site, which was the South Staff site. Those of you who've done Severn Trent Water, this is High Teeth to Meriden Main. Massive, big resilience project they've got going on. They want a current flow of just under 27 megalitres going one way, then we can increase it to 40 and then reverse it. Use the same principle. This period here is over a month. They slowly increase the flows, drop them down. They were able, you can see the results of the turbidity, plot down here, we can model it. They were able to remove material so that they can allow these higher flows. Not a single complaint from any of this work. The model, again, it's a very complex main list, but we can pick up all these different events, give or take. And again, effectively the same parameters. We've seen these same model parameters for all of these different mains. Now, because we've seen the same parameters, that simply means what we can actually do now is put in all these different scenarios. So I could work out, and I can go away and do it now, when they need to increase the flow, the gaps between the need to do it, how often they need to do it, and with that information I can then put in cost information, so I can actually work out whole life costing and costs of doing this work. Now, of course, if they change the treatment works as well, or maybe remove a section of cast iron main, you would see an improvement. So these maintenance intervals get larger, so you can then re-evaluate the costs. But you can start to see now, is it worth spending X million, maybe improving treatment works, or can they just manage their networks just by managing the flows? Okay. Machine learning, this is another way of doing it. Machine learning, very simply, takes the flow data, looks at stability data, and then predicts the next step. There's a number of different ways of doing it. Once it's got the next step, then predicts it forward again. So you got that. So, let's look at a forecast horizon, a full step. An interesting example here, this is from Yorkshire Water, I'm trying to pick any company. Again, this is a flow conditioning exercise. What you can see is they increase the flow gradually over a period of time. Each time they do it, over a couple of days, they get a turbidity response. But then the turbidity response drops off, so they know they can maintain that flow without a risk. Okay? And here's the model. This is a simple model working through. This is predicting 1 hour ahead. And this is the very basic model. We've actually got a lot more advanced than this now. So we can certainly predict 1 hour ahead. And not surprised, you go 3 hours. It's not very accurate, but then the data we're looking at is unfiltered. It's very noisy data. We've not treated the data. 3 hours is still close enough. And then when you go to 6 hours, it starts to lose it. But we could say machine learning can do turbidity. If you could predict the flow, and that's almost impossible, you can forecast up to 5 hours plus in the future. But certainly this could be used for real-time alarms. So basically, what you're saying is you could learn the system, and then it will say, well, if you have this flow, then you're going to have problems. Or it can do different scenarios. So, and that's very simple coding. You can do any flow turbidity profile with the models in place. Okay, so it's been a very quick fly through a lot of aspects. There's a huge amount of other sides in the background. But a couple of key points then, just to summarise. The water networks we're dealing with are massively complex ecosystems. They adapt to change, like you and I, we do. We adapt to change. But they're sensitive to change as well. So any type of change can cause problems. But if it's done carefully, if it's done managed, we can use that to our benefit. Now, material accumulation, the rate at which these assets deteriorate, is very much a function of water quality. So if we can improve water quality, then we can certainly have one of our systems. And my biggest concern, I've been saying for years, in fact since I started with companies, is mainly iron pipes. The big problem is corroding iron pipes. Well, they are worse in a number of ways. A, because we said it's a shear stress system. So if you've got a corroding iron pipe, it's very rough. So any slight change causes massive difference in shear stress. They've got a hugely increased surface area, all the corrosion, and they're adding so much material to the network, affecting everything downstream. I've been saying for years that we should reline, remove, whatever, cast iron pipes. And discoloration behaviour, or water quality, is predictable. So companies now can do proactive management, which does give long-term benefits and significant cost savings. I would caveat that by saying 20, 25 years ago, people who used to operate these systems used to know their own systems. And they actually knew all this. They didn't probably know the science behind it, but they understood that they had to change there'd be problems. But as companies, as an industry, we've taken away, we've tried to centralise it, we've removed all the people who knew these networks. I've been lucky in my research actually just going out and collecting the numbers, to actually go back and say, well, the guys who were operating these systems 20, 25 years ago, who knew their networks, were doing a fantastic job. It's one of these things we go back in circles. But this is the evidence base, which, again, with effective monitoring, what you do, with the turbidity traces, you've got the flow and turbidity, you can actually then go to regulators and say, I know my system can operate at this flow, I have the evidence. I have the evidence this pipe can clean because there's no turbidity response, there's no discoloration. Okay, I think that's it. I could be talking. I hope that's slightly different off track to what you may have been hearing today, but I think there is implications and relevance, certainly how water we drink and how companies now operate in their systems.